Thanks for the introduction, Elliot. So my name's Stephen. I work at a company called Ravelin. I co-founded that about 3 years ago, and I'm currently sort of managing the fraud detection team in Ravelin. So at this point, I've said Ravelin multiple times. That's not a word that anyone would really understand. What is Ravelin? So it's a credit card fraud detection platform for merchants. So if you think about if you're running an app, once you get successful, there are some bad people in the world, and they might like to use stolen credit cards on your app to get free things. So let's say we have a food delivery product. If someone uses a stolen credit card through your app, you might think that Visa pays for that or the banks pay for that, and as a consumer, you'd be right. But unfortunately, as a merchant, you bear the cost of that in something called a chargeback. So if you think that you only make a small margin off every transaction that you make, with the chargeback, you have to pay the full cost plus £15. So this kind of leverage factor means that the costs of fraud that your business faces can be sort of like actually make a material impact on your net revenue very quickly. So what does Ravelin do? Essentially, we consume information about your customers and what they're ordering and the devices they're using and their IPs, etc. And we try and score that for the probability that that customer is a fraudster. And the good thing about that is we can sort of selectively apply friction to each person in the process. So if you think about sort of maybe 5 years ago, if you were very risk averse, you'd say, I don't want any chargebacks. I'm going to put everyone through 3D Secure or verified by Visa. The problem with these programs is, no one really remembers what their 3D Secure password is. It's something about your cats, cats, mother-in-laws, color of their eyes. Like, it's just so obscure that I always forget it, and I just sort of go, sod this, I'll use something else. We can use machine learning to predict who's a fraudster and then block them from using the service or add some friction, or for the vast majority of the customers, just let them through with no hassle whatsoever. So what does that involve from a technological perspective? So we sit in the in the transactional flow, which means if you want to take money from a customer, you'd ask us first whether you should do that. And that means we have to be really quick. We have to be sort of 95 percentile, under 500 milliseconds of latency. So we need to be making decisions quickly, and we're constantly making decisions. We're doing tens of millions of pounds worth of transactions through the platform every day. Our decisions materially affect people's bottom lines. So we have to be sort of very sure that we're doing things right and going in the right direction. So machine learning is a great way to do this sort of scoring. Previously, it was done by rule engines and expert systems, but we think machine learning is a better way to do the majority of that. And just for some context, fraud is a particularly sort of fuzzy machine learning problem because you don't get the labels, sort of whether a transaction was fraudulent or not, for up to 90 days after you've made your decision, which is kind of a bit of a pain if you want to evaluate stuff online, because it means that it's a lot harder to do things like A/B tests online because you have to wait 3 months until you get the feedback. And if you're waiting 3 months, then that means you can do 4 model deploys a year, which is not great. I want to talk about how you can deploy machine learning models faster. If you think about kind of machine learning teams, I might just be kind of plucking this out of thin air, but I think a sort of good deployment cycle for machine learning teams is probably a few times a quarter, say 3 to 5. These are viewed as kind of risky events. So you'd be doing, a lot of big changes bundled up into one thing. You might be running A/B tests on recommender systems for a few weeks to see if one's better than the other. What we've decided to do is essentially deploy new models multiple times a week, because we're constantly getting feedback in from our clients about this person is good, this person is bad, we have good and bad transactions, and we want to ensure that our model doesn't drift from what fraud looks like in the real world. We want to be sort of up to date. So we just have a team of 4 people doing this. So we have to make sure that we're minimizing the sort of toil and repetitive work that each person has to do when they're deploying models. I think this is a bit of an anomalous day, but I managed to deploy 4 models this morning before I had breakfast. So that's the sort of speed we're attempting to go for. So I really like this quote. It's by Martin Fowler, who has a lot of great aphorisms on software engineering. But if something's really hard, you should just do it more often. And what that means is if you're doing something slowly or not very frequently, you're bundling up more risk into each deploy you do, which means each deploy is scarier, which means each time you take thinking about whether you should deploy it takes longer. And you get into this sort of horrible feedback cycle of not shipping stuff. Whereas if you keep the changes small and you keep the differences between your models relatively small, then you can sort of have this gradual improvement. So this is definitely a mantra that we've applied at Ravelin. So I'll go into the technical details now. So in order to deploy multiple models sort of every week, we have tried to automate basically everything that is boring, everything that is error prone, everything that we don't want to do. So we have a Python Go hybrid sort of pipeline that we package up into Docker images. These are run on just really chunky machines in Google Cloud. So when we want to train a new model for a client, all I'd have to do is I hop onto our internal command line tool called rshell, and we just do sigint machines create. I just name my machine, the Docker image I want to run, and the client that I want to train a model for. Now, essentially, give it a couple of hours, and I will have a fresh model with all of the evaluation metrics and everything I need to know whether this model is good or not. And this definitely wasn't always the case. We'd be training stuff in IPython notebooks. Someone would be running a random command somewhere, and then we would sort of ship it, and stuff wouldn't work. And then we'd be trying to figure out what was the random command that we ran that made stuff not work. I think we should not be treating machine learning as a special snowflake. Apart from software engineering, we should be trying to sort of ham it more into the software engineering world. So what does the output of our pipeline look like? So once we've trained a model, we've archived all of the training data to Google Cloud Storage. Everything in Ravelin runs on GCP, including all of the live stuff. So we have all of our training data, and each step of our Luigi pipeline, each intermediate step. So we would be able to delete parts of the pipeline, rerun it, and basically get exactly the same answer. At this point, we've trained a model. We've got some performance metrics. So these would be things like precision recall, various metrics around the number of positive, negative examples, the sort of boring stuff that you want to, there's some interesting stuff in there, but there's some underlying trends that you want to keep an eye on. So we post this all to BigQuery as well, so we can just make dashboards out of it. One of the really cool things we've done recently is that gets then auto-deployed to our live cluster of machines that are scoring models on a queue. So essentially, we can just say, we just deploy the model, and that gets deployed in seconds to sort of an asynchronous queue-based system. So we're scoring everything, and then we can join up and do analysis later on. But the key thing here is that we get a HTML report, which is, I would say that's the biggest change that's really helped the team. So I'm going to go through a bit of the details now. We get a HTML report posted to us in Slack, and this is really, really helpful because we can then sort of codify all of the things that, we can codify what success looks like and what failure looks like into higher level kind of unit testy style checks. So we don't have to have people going through all the raw metrics and saying, okay, if this thing is good, then we should deploy it. If it's bad, then it's not. We just sort of codify everything up into these pass-fail states. And we can quickly figure out if the model is good or not. So, top one is test PRAUC. Asserts is a really useful concept that we've used to figure out. In the absence of true or very trustworthy labels, you have sort of fuzzier labels in fraud detection sometimes. We sort of call asserts our golden set or our validation set. So if the numbers sort of go up on there, or we want to spot all of the fraudsters and we want to not catch any of the genuine people, essentially. So if those numbers go up, then we know that we're going in the right direction. And if test PRAUC goes up, but assert performance goes materially down, then we know we're definitely going in the wrong direction. So this is the rank of the features that were used in the old model and how those have changed to the new model. So if we have a model that we trained a week ago and a model that we train now, and the features are totally different, the most important ones are totally different, then that probably signifies there's some instability in the data that we have, or at least something worth paying more attention to. And the way you consume scores from Ravelin is by things called actions. So we basically say you should allow this customer, you should review them, or you should prevent them. And we can codify up this into, of all the people we scored, how many times did those recommendations change? Which means that is a great metric for risk, because it's how different is our previous model to our new model. And if it's not changed very much, well then we're not changing the world in terms of fraud detection, but we know that the risk of deploying that to live is really quite low, because we're not going to start saying all of these people we historically said were bad are now good, etc. So we've also got a summarization of the biggest changes from the old model to the new model. So there's a list of customer IDs here. I just hit that with a slide on Google Docs, but we would have links to our own internal dashboard where we could check the customers. And these are saying, you should probably review these people, because previously you said one action and then you actually said the other. And the reason that this is really nice is because you can use this in your golden set and just sort of say, okay, I think we got this one right. So put that in the golden set. I think we got it wrong. Put that in the golden set, and then you just keep essentially improving your golden set of customers that gives you a better estimate of what your model is doing and how it's performing. It's just sort of critical for figuring out if you're going in the right direction, because we have so much data, and not a huge number of people working on the team, so we don't want to be crawling through individual examples and rows of data all the time. We would try and, we'd like to stay on the aggregate level as much as possible. I've been doing this for about 3 years now, and kind of just been doing machine learning most of the time with some software engineering. And I think these are the principles that have made our team pretty successful. So I would say prefer summarization over absolute sort of raw details. So machine learning is a complex problem as it starts with. You've got tons and tons of data, tons and tons of examples. Just keep things as simple as they possibly can. So reports, graphs, little cute green ticks or red crosses, instead of just going through all of the logs of the training examples. You want to minimize interpretation needed to ship new models, essentially. Manual toil. I don't know if anyone here has read the Google SRE book, but a lot of the toil stuff in there really resonated with me, because there's a lot of manual crap that you kind of need to do when you are shipping machine learning models. You kind of need to get the data and you need to transform it and train a model, and then you might need to calibrate it and do all of this stuff. Computers are really good at that, so just get them to do that. Because otherwise you're going to get it wrong, and you'll also have unhappy people as well. Also, just automate everything, because like I said, in the previous point, computers are good at this stuff. You can be doing much more impactful things. So building new signals for the models, or you can build a completely new pipeline that's spotting something different. You just don't need to be running all of these commands yourself. I kind of just want to make model deployment boring. So my dream is that I come in the morning and the rest of the team has just redeployed all the models for all of the clients, and I didn't notice anything went wrong, and people, they didn't treat it like it was a big deal. And I think we're still a bit of a way away from that, but we're certainly on the right track. Yeah, sorry if I rushed through a few things there, but I would, I have the obligatory sort of thing to do, which is, if any of these principles are interesting to you, then we're hiring junior data scientists. We're really looking to sort of train people up, give them experience and kind of going along with this stuff. So please come talk to me after this. And if you're basically any kind of software engineer, we have DevOps, we have front end, we have back end. It's just everything. So if you're interested, talk to me after this, or you can apply on the Angel list link as well. So thank you everyone for listening to me.